so here we've got a space probe. It's moving along through space at 160 meters per second. And then there's an explosion and it fires out a capsule. Okay, so a planned explosion meant to fire out this capsule. And obviously that explosion releases some energy. So the whole point here, first of all, is to calculate the velocity of this capsule. And then we're going to look at the kinetic energy before and after the explosion. So the first thing we can say is we're going to need to use conservation of momentum here. So we know that the momentum is conserved. So the momentum before the collision and the momentum after the collision must be the same. So due to conservation of momentum, momentum before is equal to the momentum after the collision. All right. So momentum, if you remember, is just mass times velocity. Okay. So momentum is usually given the symbol P, and it's mass times velocity. So before the collision, the mass is 500, and we're going to multiply that by a velocity of 160. Now, we're going to decide, and you can make this decision, it doesn't really matter which way you decide this, but we're going to decide that velocity to the right is positive, okay? You could say velocity to the right is negative, it really doesn't matter, but if velocity to the right is positive, velocity to the left is therefore going to be negative. So the initial momentum is 500 times 160, and then the momentum afterwards must be equal to that. Now the momentum afterwards consists of two components, or two aspects, two components. That's probably a bad term actually. The point is the momentum afterwards, there's two objects with momentum. There's the space probe and the capsule. So the probe is moving to the right, and we don't know which way the capsule is moving, but you can probably guess it's going to be moving to the left. But we'll call the velocity of the capsule V. All right, so the momentum afterwards is the mass of the probe multiplied by its velocity. Okay, and then also the momentum of this has to be taken into account. So it's going to be the mass of that, which is 150, the mass of the capsule, times by V. So that's the equation we've set up. Some people like to do this in parts. I like to set it up as one big equation. Okay, so 500 times 160 gives us 80,000. Okay, 350 times 240 gives us 84,000. And then we know that also, you have 150V added onto that. So all we've got to do now is rearrange the equation. So if we rearrange this, we're going to find that 150V is equal to 80,000 take away 84,000. So basically I've just taken that over to the other side. It was a positive on this side, so it becomes a negative on that side. So that means that 150V is equal to minus 4,000, and therefore V will equal minus 4,000 divided by 150. Okay, and that's going to give us our answer, which comes out as minus 27 meters per second. Now we've only quoted this to two significant figures, but that's absolutely fine. That's what it says in the mark scheme. But the point is here that this is a negative value, okay? And that means that the capsule must be moving to the left.